Hi, sir. Hi. Yeah, sure.
Hi everyone, welcome to the ICTS String seminar. So today we have Chethan Krishnan from IISc who will be talking to us about fuzzballs and random matrices.
All right, thank you. Okay, so let me start by thanking you for inviting me. So this is a talk. Unfortunately, Loga has already heard it, but I decided to give it anyway because hopefully I can get some feedback from Ashok or about fuzzballs. So that is my primary motivation for choosing this particular topic. So this is some stuff that I have been doing with these collaborators in the last 1 year or so. And so the pictures that I'm showing here are taken from Suman's notebooks. And also I should emphasize that Preetham, who's an undergraduate student, was the first one to see this particular linear ramp that I will talk about. So, okay. So, right. So with that sort of quick introduction, let me go ahead. So I'll start basically by giving a general overview of the fuzzball philosophy, even though I'm not so much of an expert on fuzzballs. And if you find anything that is objectionable, please feel free to correct me. And eventually the idea is that, so the calculation that I will do will be a very simple calculation. And I think the biggest sort of virtue of it is that I think it is quite robust. And in that sense, maybe it is useful for something or other. Okay, so let me start with the observation that the black hole horizon is a place of controversy. As we all know, I was hoping that Suvrat would be here, but unfortunately he's not around. And the debate has gone through various iterations and has recently been revived in the context of the information paradox. Starting with Page, Mathur, and this AMPS firewall business. And let me take this. Yeah. So today I think what we'll do is we'll view this as a question about the meaning and interpretation of black hole microstates in string theory and in the bulk. So this is what we would like to ultimately go towards. And these have the idea is that these states have the same macroscopic charges as black holes in the bulk, but at least in the supergravity approximation, candidate microstate solutions cap off basically before the horizon. So this is the general philosophy that one hears in the context of fuzzballs, and this is sort of the foundation of the fuzzball program. So let me, because it's a somewhat the opinions are divided about what the status of fuzzballs is. And since I'm kind of an outsider, let me start by listing a few pros and cons about what fuzzballs do or do not. And so the first observation that I find interesting about fuzzballs, and I think it is quite a non-trivial fact, is that the fact that these solutions exist in string theory or supergravity is non-trivial. Because in classical general relativity, they are ruled out by no-hair theorems and the like. Okay, so this is the fact that they exist should surprise us. And the second fact, which is something that I also find interesting, is that these solutions, they are not distinguishable from black holes, at least far away from them. And so the classical solutions, of course, they start disagreeing before some Planck, even before the Planck distance, and in that sense they are more questionable. But just the mere fact that in many of these solutions they approximate black holes all the way to the throat, which is the ADS2 part of an ADS3 geometry, is, I think, worth noting. So the fact that they could have differed from a black hole far away from the black hole, but they don't seem to. So, and I think in that sense, there is something about them. I don't think that you can think of them as solutions which have nothing to do with black holes. They clearly have something to do with black holes. And so it behooves us to sort of understand what that is. And the second fact is that third fact is that there are whole moduli spaces of such solutions. So this is necessary if they have to be interpreted as microstates of a black hole. Okay, so at least in the classical limit. And in some limited cases, by which I mean cases where at tree-level supergravity, at supergravity without higher derivative corrections, the horizon is there is no finite horizon. You can actually count this entropy, and you find that this matches, at least in specific cases, like in at least in one specific case, it matches precisely with the counting of entropy. So these are the pros that I would list, but there is now I would list some cons, so to speak. Yeah. So the statement is that. So how do I go back? So the statement is that so the Rishkov's counting basically gives you the scaling of the two-charge black hole. So it is not for the one which has finite horizon. So the only thing I wanted to emphasize that even the numerical coefficient can be matched for the K3 case. So that's yeah. So but there are also flies in the ointment, which is that one of them is that microstate solutions are only known for BPS black holes, and an obvious criticism, which I guess I mean this is something that I don't see it discussed as much. I mean I've talked with Subrat about this for a long time. But it's something that I don't see discussed as much, but probably I'm sure everybody in the community knows it very well, is that an obvious criticism is that supergravity microstates, if the profile functions are sufficiently complicated, then the curvatures are Planckian, and in that sense, they're not very interesting. Okay, so that's one obvious criticism. But I guess the reason, I mean, so my suspicion, the reason why it is not really, it's discussed, it's not that it is not discussed, but it's not emphasized as much as probably it should be, is that the solutions are BPS, and somehow you expect that even if the solutions, even if they are not completely well defined in supergravity, you expect them to exist in the full string theory in some sense. So of course that's so they're BPS protected solutions. So and then there has been criticism by Ashok that these solutions, criticisms or arguments that they should actually be added to the entropy of the black hole, depending on the duality frame. We can discuss that, but there are some counter examples and counter arguments as well about this. So whether you should count them as a proxy for the black hole, or they should actually be added to the entropy of the black hole is, one could say it's debatable. And in the three-charge case, so the three-charge case is the case where the horizon size is finite in supergravity, and in these cases, the solution spaces are discovered so far, and I suspect probably one can show that in supergravity you would not be able to find all the entropy of the black hole. So these are the sort of the conventional objections, if you like. And then, I mean, conventional means, so the technical objections, but then there is also the obvious one in some sense, which is that if you have microstates that cap off at the horizon, it raises obvious problems because, most of the things that we know about black holes are based on the fact that the horizon is smooth, and Hawking radiance is a direct consequence of smoothness of the horizon, if you wish. And and these are all questions that horizon, geometries which will cap off before the horizon can potentially find challenging. So it remains to be seen how one has to, if at all, one can have a smooth horizon physics in some way out of this, is a question that one has to deal with. And a related problem, essentially the same problem, is that more generally the problem of understanding various aspects of horizon physics in a dynamical setting via an ensemble of microstates. Instead of, so the idea is, a black hole, the dynamics of a black hole, microstate, it presumably should be replaced by an ensemble of these microstates in some suitable sense. But how exactly one should do it and what is the kind of questions for one has to do it is all of these are essentially left open. Okay, so okay.
As far as I know, these fuzzball solutions are constructed. As far as I know, the fuzzball solution, they are constructed only in a high codimension subspace of the moduli space, right? And I mean, in general, one would expect that if you go to a generic point in the moduli space, all of these may exist.
Right?
It's not clear if they have non-zero index, for example.
Yeah, but I think that so for instance, I'm sure that you're aware of this paper where they compute using the superstrata approaches. There is at least there exists solutions which are deep in the black hole regime. So there is an explicit paper where they construct it, and the claim is that these states actually will contribute to the elliptic genus, for instance. So there is a claim of this nature.
Yeah, but how is that claim justified? I mean,
so they explicitly construct, for instance, the coherent states corresponding to this construction on the CFT side. So they can map these things one to one. So, I mean, I'm not defending the claim, but I'm just saying that the claim is there. So, yeah.
Because typically I would think that this is like, I mean, in n equal to 2 supergravity, you can construct a lot of multi-center solutions.
Yeah.
Most of which don't exist in the.
So this is specifically, so they have 2 Gibbons-Hawking centers. So that's the kind of solutions that they construct here.
Okay.
So
there are many examples of 2 Gibbons-Hawking centers in n equal to 2.
Yeah.
Right. Which don't exist in n equal to 4 or n equal to 8, for example.
Yeah.
In n equal to 8, none exist. In n equal to 4, only very special ones exist.
Right. Yeah. No, I want to emphasize that I'm not defending it too much. As you will see, my calculation this is just to give a context and to kind of make, I also wanted to hear your opinion. So, but the calculation that I'm going to do is extremely simple. You will see that it's extremely simple, and its point in some sense is that it makes maybe its simplicity and the fact that it seems robust is of some interest. So this is what I would say. So I agree, yeah. So I'm kind of torn. Let me put it that way. So, but yeah, I hear you. I agree. So, yes. So the converse. So I want to start by giving a sort of a summary of both the pro and the con. And the con side is basically where so there is 2 approaches, I would say, for black holes and quantum gravity, and there is the second approach is basically what I would call the semi-classical approach, and it draws inspiration from semi-classical gravity and let's say holographic entanglement entropy. And there are interesting results. One of them is basically the fact that there are you can identify chaos and scrambling and hints of random matrix behavior at the horizon, and so this is some so you expect that black holes to be scramblers in the sense of you expect them to be thermodynamic objects, and a recent success of this approach is basically this calculation of the page curve of an evaporating black hole, and it can be reproduced by using ideas from holographic entanglement entropy, which were introduced for other reasons. And I think that's interesting that it is based on other reasons that it was introduced, and not specifically for solving this problem of page curve. So this quantum extremer surface was introduced for other reasons which are independent, and that is able to solve this problem. So that's I would say it's a pro. So pro for this semi-classical approach. So the challenge is, of course, that while the final page curve in the island paradigm is comparable with unitarity, so the detailed emergence of unitarity in each epoch of Hawking radiation is challenging. So and the reason is, of course, that these calculations are fundamentally Euclidean calculations, sort of masquerading as Lorentzian calculations, and so it's not very clear whether one can have a fully Lorentzian calculation which gives the page curve in a straightforward way. That would be nice to have. So that would be a real resolution of the information paradox in some sense. Okay, so one could say that so there is some evidence one could say that the semi-classical gravity should be viewed as a proxy for a time average, an ergodic proxy for a time average, and during each epoch of Hawking radiation. And by each epoch of Hawking radiation, what I mean is something that is roughly of the page time. So the time scales involved for changing the mass of the black hole in a substantive way. So the final point in some sense is that in both fuzzball approach as well as the semi-classical approach, the emergence of smooth horizon is still quite mysterious, and we don't understand what's going on. So that's sort of the punchline. So a natural goal that one might aim for is what is one to make of the situation, right? So what is one to, so how are we supposed to reconcile? So there are 2 approaches, both of them seem kind of half successful, but not really fully satisfactory. And so I think one thing one could try to do is maybe take some lessons from one side and try to apply it for the to the other side, to get some lesson from one side and try to apply to the other. So, and not just simply because we wish to be reconciliatory, I want to emphasize that, because it is not just, it's somewhere in the middle of two ideas is not necessarily where the truth is. So, but, both of these things seem to have some interesting results, but may not be fully satisfactory yet. So they both have profound challenges. I think it's a fair statement. But they also have arguably successes. So how might one go about trying to synthesize the two viewpoints is one main question we have. So the way we'll approach this, and can one reproduce the success of one approach using the tools of the other? So this is the question. So, and we'll take a step in this direction. So specifically what we'll do is we'll reproduce the level spacing distribution and spectral form factor, which are two diagnostics that I will explain momentarily. Expected for black holes from semi-classical arguments, but starting from fuzzball. So this is what we will try to aim for. So a linear ramp in the spectral form factor and level repulsion are supposed to be random matrix diagnostics. Okay, so if we can reproduce them from, let's say, this fuzzball thing, and by fuzzball, I kind of want to emphasize also that what I mean by fuzzball is really a stretched horizon for the purpose of my talk. So, and you will see that there is a certain robust way in which these things are realized when there is no interior, and that I think is the kind of the point of the talk. Okay, so did I go too far? How am I going? Sorry. Yeah. So so this is the sort of the setup. And so, yeah, are there any questions about the general setup? This the stuff so far was kind of like an overview, and now I'm just going to tell you what the calculation of the results are. Okay, so if there are no questions, so let me just define what the spectral form factor is. I'm sure that you have seen it many times in the last few years, and it's essentially defined using this this analytic continuation of the partition function in beta. And it's defined like this, and this is some object. And why is it? It's kind of like a proxy for a 2-point function in some ways. And so the idea is that you can look at the time behavior of this quantity, and you will find that there are some signatures that you will hope to identify with random matrices and chaos and so on. So that's the idea. Okay, so what is the general expectation for this? In random matrix systems, which are random matrices, we will use it interchangeably with the existence of chaos for many purposes. The spectral form factor has a distinct linear ramp on a log-log plot. Okay, so what that means is, so there are this spectral form factor, if you plot it on a log-log axis, what you find is that there is a slope, there is a ramp and a plateau, and the ramp has slope 1. And the slope 1 is important. You can find various spectral form factors which have which behave with things that look approximately like a ramp, or maybe not approximately, kind of with behavior which is somewhat analogous to the ramp, but the fact that it has slope 1 is quite supposedly quite important for random matrix for it to be a chaotic system. So the expectation is that fuzzballs cannot do this because the spectrum of normal modes of a capped off geometry is roughly evenly spaced. So essentially, because if you have a standing wave, basically all the levels are kind of evenly spaced, so it's a bit like harmonic oscillator. So, and we expect something akin to an integrable system. In other words, we expect level spacing distribution without repulsion and spectral form factor without a linear ramp. So level spacing is basically just the the differences in energy levels. You plot the distribution of those energy differences, and you find a certain shape, and I will show you some examples in a second. So these two features are kind of like the conventional random matrix diagnostics, if you like. And so these explicit fuzzball geometries where there is, if you put a cutoff, you typically do not expect them to have this property. So yeah. So, but of course, we have one problem, which is that most of the explicit fuzzball geometries, by which I mean these BPS supergravity solutions that people have constructed, they are inaccessible at finite temperature, at finite temperature, because these are BPS solutions and so on. So yeah, so this is the sort of the heuristic expectation. So we want to kind of try and reproduce whether we can get this sort of a result by starting with a finite temperature object, because we are interested in not just BPS solutions, but also as models of real black holes. Okay, but yeah, so the point is that the expectation that we have, this expectation of if black holes are supposed to reproduce random matrix or chaos behavior, these expectations are quite generic. So generic and robust. So in that sense, we expect these features of black hole microstates at finite temperature to be somehow, we shouldn't have to do too much in order to get it. So we would expect that it's if we have to do something elaborate to get it, it's probably not very interesting. But if we can get it by doing something that is sort of well motivated and sort of simple to try, then we would expect that maybe there is something to be something to it. So the thing that we will try is we'll simply chop off the geometry before the horizon as a toy model for a fuzzball and see how the modes behave. So this is what we will do. And yeah.
So you're kind of saying that because you don't know fuzzballs for finite temperature
Yes.
Objects, you're going to define something that will be a proxy.
Yeah, so I'm saying that that's right. So I'm basically saying that like if we can, so in this talk, largely what I mean by a fuzzball is just a stretched horizon. So if you have a stretched horizon, can we reproduce a linear ramp, for instance?
But in what sense does that capture multiple geometries? You're just going to put some.
So you will see. For instance, if you have a probe scalar in such a geometry, we can actually try to, one of the things you will see in order to get a level repulsion, for instance, the boundary conditions that you're imposing at the cutoff can have an angle dependence, for instance. So that will be the analog of a profile for us. So for instance, if you put a cutoff, you will immediately see a linear ramp. That's one of the punchlines. Let me just say the punchline already. So, and that's the reason why that may not be completely trivial is because it is generally believed that linear ramps are not easy to come by if you don't have random matrix behavior. So it's in fact, people have gotten angry with me for seeing. So in one example that we will see, you will see that it doesn't really have a random matrix like level spacing distribution. What we will see a very clear linear ramp. So this is, I think maybe you can ask that question in a bit and it will make a bit more sense. So the point is that we want to do things which seem quite well motivated and the first thing one might try. And if we can get this linear ramp and level repulsion, then it may be of some interest. Otherwise, I think if you have to engineer it too much, then I think it is not very interesting. So this is the sort of the point of view. Obviously, if you're putting a cutoff at the horizon, in general relativity, you can't justify it. It's a completely, uncontrolled calculation. But the motivation for that is that if you do it, does it lead to something interesting? If it doesn't, then it is, So that's the idea. Yeah.
So this,
Let me just get some water.
When you are seeing this ramp behavior in all these random matrix systems, is that also a diagnostic that there are that many Bekenstein-Hawking number of states in the system?
I don't know whether that is automatic. So what I will actually, one of the things that we will find is that, so one of the reasons why people had this expectation that you should not see a ramp is because if you just think of it as a set of modes in a standing wave kind of a thing, like let's just think of ADS. ADS, the spectrum is basically linearly spaced. So, and it's essentially identical to the harmonic oscillator. So you would not see any interesting behavior. So that was roughly the expectation. So, but what we find is that if the cutoff is close to the horizon, the dependence on J directions is non-trivial. So this is what we find. So the omega, the normal modes. So what we will be defining are basically normal modes of the black hole with a stretched horizon. And these normal modes have the sort of linear dependence on N that people have anticipated, but at the same time, they have a non-trivial dependence on J, because of which you end up finding this linear ramp.
What is N for you?
N is basically just the, whenever the normal modes are counted, right? So like, it's like the principal quantum number, if you like. So that's N. But J is the angular quantum number.
Right. No, so that's what I was, because when you talk of
Right.
random matrices, and I can ask this later also, but when you talk of random matrices, you normalize it by a capital N, which is the size of the random matrix.
Sure, yeah.
Roughly like e to the S naught.
Right, yeah, yeah.
So, but is that something you put in by hand?
Yeah. So see, if you have, so I think what you're talking about is basically, so in a probe geometry, so if you're doing a probe calculation, it's the n, that n is not directly related to the entropy of the black hole, right? Because we are doing this is a probe calculation, and so we can, it's also the thing is that entropy gets divided out because it just normalized, and the ramp is not, it's not directly related to that, but I will answer that eventually, because ultimately I think that the answer is yes, in the sense that the entropy is what controls the ramp, but it's in an interesting non-trivial way, because the thing is actually sensitive to the black hole, and the entropy that you're talking about, though, when you put in these modes, is just the dimensionality of the spectrum. That's not what this is. We need to be sensitive to the underlying black hole geometry, and that is what actually controls the ramp. So in that sense, yeah, I think ultimately the answer to your question is yes, but it's an interesting way. So yeah, because yeah. So where was I? Right. So yeah. So the reason why we expect is because of we expect that we can make some progress is basically because the calculation can be, if we can do something, the expectation is quite a robust semi-qualitative one. And so maybe without having like full control on these fully quantum fuzzballs at finite temperature, maybe we can make some progress. So that's the sort of the hope. So this would mean that we would be computing normal modes, is what I was just saying, of a black hole instead of its quasi-normal modes, because we are cutting it off right before the horizon, and we can impose Dirichlet boundary conditions at the stretched horizon. And I will, along the way, we will qualify some of these things. And this is Tufts' original paper, is the oldest paper, I think, where the stretched horizon has been seriously considered. And we will first do this for a horizon where the wave equation is quite tractable. So, right, so this is the BTC black hole. So you can solve the wave equation. There's nothing going on in this slide. I'm just separating variables and so on. So, and again, I want to emphasize the calculation is extremely simple. Okay, so the numerics of determining the normal modes is a bit somewhat painful, but conceptually it is extremely simple. So the radial part takes some particular form. I have set the horizon radius to be 1 here. I think you can make it arbitrary. And the point is that, so we demand two conditions. One is that there is normalizable boundary conditions at infinity. And the second is we will demand a Dirichlet condition here. And both these conditions are not super important, but I will explain in, so you will see that both these conditions, one has to be at near the horizon, and the other has to be at infinity, and that's pretty much all one wants, and modular one caveat that I will get to eventually. So when you do that, you find there's enough constraints in this problem to get you the normal modes, and these are the normal modes that we will be considering. Yeah, go ahead. Yes, but you can set it to not 1 if you want. So I just said it because of, it just happened to be, that's the first place where you did it, but you can change it. So in that equation, yes, L and RH are both 1.
I can restore both and.
Yes, you can, yes. So, no. So I'm doing BTC, this is just the radial part of the equation.
Angular part.
So angular part is, so this is just e to the ij psi, right, this part.
So that doesn't enter the.
It does, because if you look at it, this V of R is a potential which depends on J. Yeah, and so this J, there is in some sense, that's a very key point, because the J square multiplies the stretched horizon size. So, and that is crucial for many of the things that happen at a technical level. We don't understand it very well because most of the normal modes themselves are numerical. So we don't understand it at a very deep level, but that's clearly important. So, yes. So yeah, so these two conditions are enough to fix a spectrum, and we find this omega nj, and n is this, let's say, principal quantum number, which is a free mode, from the mode condition that you get, and j is the angular quantum number. And so when we compute this, so we find basically a wrinkle in this conventional expectation of spectral form factor. While it is true that the spectrum has linear dependence on the n quantum number, which is sort of the canonical expectation, let's say, the dependence on J is actually non-trivial. And so basically we are doing a calculation like this. And this is kind of answering part of the question that Rajesh was asking, which is that in order to do this calculation, we have to put a cutoff in J and N. So these are the normal modes. At some point, you have to do a cutoff. And we have checked that as you slide the cutoff, the qualitative results are not affected. And besides, getting a linear ramp, even though we don't believe it is that difficult now, it's generally believed to be not an easy thing if you're not putting in some form of random matrix behavior. Because note that we are working with a free theory. So we are putting in a free theory with a stretched horizon, and we are going to find a linear ramp. So in a sense, that's like if you're finding it, it's not supposed to come out easy anyway. So it cannot really depend on the cutoff a priori already. But we have checked that if you slide the cutoff, it doesn't affect the results.
Why do you need a cutoff?
So just for computing this, because we are plotting this numerically, right? So you could in principle come.
That exponential suppression is not enough to.
No, it is not because of the suppression or anything. It is just that this quantity, if you want to plot it, we have to actually compute it with some finite. It's a numerical calculation, right? So we have to stop somewhere, that's all. It's not a conceptual deep issue. It is a pragmatic thing. So, but I'm just saying that we can check that it doesn't depend on the cutoff as we slide. The qualitative feature doesn't depend. That's the point. So, yeah.
But it's a convergent sum, right?
Yes, if it is, see, that's a slightly tricky question because beta is, can be zero in principle. So many of the statements in random matrix literature, for instance, is at beta equal to 0. So if beta is 0, then we have to worry about whether it is, what kind of a function this is and so on. But in general, yeah, we're not doing anything different from what other people are doing, but yeah, we can plot it both for beta non-zero as well as beta equal to 0, and beta equal to 0 is largely what I will show you. So, but yeah, so that's sort of a standard thing. And I think the most robust analytical claims about the spectral form factor are at beta equal to 0 in the random matrix literature. Because I don't think it is, people sound very confident they talk about it, but I don't think they understand it very well. I often feel like, because it's a thing that, so because I have been told very confidently by various people who know this very well, that linear ramp is not that easy to get. Unless there is a random matrix around, you won't get it. And in this particular case, I'll explicitly show you an example where at least the level spacing is definitely not of a random matrix, but you will get a linear ramp. So, and in fact, we have simpler examples of that now because we understand the spectrum a bit better. Okay, anyway, so this is an example of the plot that you can get. And you can fit lines on this, and you will see that this is actually a linear ramp. And the key point in some sense is that the spectrum in the J direction is key for getting the ramp. So this is the first sort of observation. You had a question?
So what sets the states?
So that doesn't really matter because all of these are logs in some sense. So are you asking? So for instance, these are some dimensionless time. I don't remember exactly what it was.
Yeah, I meant the relative heights.
So the relative height, the Plato height is related to the e to the s naught that you were talking about, which is, but that s naught is not directly related to the entropy of the black hole.
Yeah, but
so
that would be related to your cutoff.
Exactly. Yes. So so the spectrum in the J direction is key for getting the ramp. If the sum is over enough J's, we always see the ramp. So this is sort of the main punchline. We'll get to a sort of a bigger punchline eventually. So it doesn't matter how many n's we keep. Often we'll work with n equal to 1. So n is this vertical quantum number, and the other one is the angular quantum number. So so by plotting a line through this ramp, we can really see that it is actually slope 1. And here I'm plotting, a sort of an ensemble average. So what I'm doing is I'm basically, what I mean by, so if you have, so we can compute these quantities for different cutoffs, the stretched horizon radii, and then we can average over them. So that's what I mean by an ensemble average. And the only purpose of doing that is to really see that the slope is 1. So this sort of a kink-like thing that you see at the top is actually an artifact of the cutoff being at, fairly macroscopic, this thing. So as you slide the cutoff closer and closer to the horizon, that you will see that sort of dissolves away and the slope gets better and better with 1. So that.
Yeah, just to ask my previous question.
Right.
I mean, there are three different heights.
Right.
There is the one you're normalized to one.
Right.
And then there's the dip.
The dip time, yeah. So I think,
the plateau height.
yeah. So the plateau height is related to the dimension that we are keeping. And so the thing that I would eventually, I think that that's, I have not thought about it sufficiently. So I think that this, so,
in the actual problem, if I remember, I have not followed.
Yeah. I'm also not an expert.
Then it goes to the S naught.
Yeah. So I think, but it depends on where it starts, though. It depends on where it starts.
So normally you put e to the 2s naught or something. That's your.
Well, I mean, e to the 2s naught, I think, is here. Here it's always normalized to 1 because it gets divided by the denominator, which is also the spectral form factor, right, at t equal to 0. So by construction, this is 1. So I think that the one free thing here is basically this guy.
Yeah.
So that I unfortunately I don't remember exactly what it is. So
it seems quite odd. Why does it turn up?
So I'll tell you at the end that if you just have a logarithmic spectrum, you can get a linear ramp. So linear ramp is not that mysterious. So if you just have logarithm in the spectrum, you will get it. So this is something which, of course, we had to go through this whole thing in order to see it. But now it feels like so one of the things that I'll say, I think my last 2 or 3 slides are sort of the most interesting slides. Maybe I think you can ask that again at the time. So maybe that will be a bit better. So
I'm just trying to understand this mathematically what you computed, normal modes. You just took that sum, right?
Yeah, that's it.
Sum,
yeah,
exactly.
it's just.
I'm trying to understand qualitatively why that sum should behave like this.
That is something that we don't fully understand. I think the ramp is, I mean, I don't know.
Because normally you would think, you have a lot of phases.
Right.
There's a linear behavior.
Yes. Yeah.
Right? When you have a lot of phases, there'll be cancellations.
Yeah.
And so it will start.
It will die.
It will start
Yeah.
dying.
Yeah.
And then I'm trying.
So this sort of thing, if this is the part which is supposed to be coming from a replica wormhole, right?
Yes.
So that part. So yeah. So okay. So I think I can tell you. So this is if you had a real genuine random matrix. So in our problem, we don't understand why it is happening. That's the honest answer. But like I think your question has the conventional answer, which I can tell you is that there is like in the this is in some sense a Fourier transform of the spectral correlation function of random matrix things, a random matrix rho, and then you have a sine kernel, right? So the sine, that's where it is coming from. Yeah.
You're not starting with
I'm not starting. So that's why I don't understand. Right. Right. Yeah.
It's a Newell problem, Newell problem.
Yeah.
You're just
Yes.
in a normal mode
Yes.
and computing.
Yes, but I'm saying that now that we know it's a logarithmic spectrum can do this, I think we can say more, and I think it'll be easy to say it, but we just found it out like very recently and we have not explored it. But from a random matrix, and this is the reason why people were suspicious of us when we were saying that this is, this ramp can come out without any kind of seemingly direct connection with random matrices. And that's because there is no scope for getting the sine kernel and everything here. It is just coming from the fact that it is a feature of the spectrum. And of course, when we were first looking at it, it just seemed like some random numbers, these omega nj's. So we didn't have a real understanding why it was happening. Now I think it is less mysterious, but I still don't have a completely satisfactory answer to your question. I think we will be able to answer it soon though. So yeah. Yeah, sure.
Stretch horizon as you are doing, but I really have a horizon.
Yeah.
And I can still solve this problem actually, for the spectrum.
Well, I mean, if you have a horizon, then you have to put boundary conditions.
Of course, that's what I'm getting to. I mean, you have infalling boundary conditions.
Yes.
But there is a spectrum. There will be
Right.
some modes, which I
Quasi-normal modes, yeah.
Exactly. Suppose you take that spectrum and compute this.
Yeah. So then it will just keep dying because that's a version of the information paradox, right? So it will just go and it'll just die exponentially and die off. So, and because they have an imaginary part.
Because of the quasi-normal mode.
Exactly. So here the point is we have cut it off before the problem. So once you grant us that, then the rest is whether it is, that's the question. So I have kind of order 1 solved my problem by getting rid of the horizon. So, but once you do that, whether it is, whether there is something interesting or whether we are, the things that we are getting worth it is the real question. Yeah, go ahead. Maybe you can pass him the mic.
Stretched horizon R naught at which you're demanding these boundary conditions. The
Sorry, can you say
the
that?
R naught at which you're demanding these Dirichlet boundary conditions.
Yeah.
Now you're saying that you're doing an average of the spectral form factor over this R naught.
So that is for just for plotting this curve. So for instance, in this one, I'm not doing that. It's a fixed some particular R naught. And as long as the R naught is sufficiently close to the horizon, this is the structure. That's it.
And so why are you doing this average then?
Why am I doing what?
Why are you doing this average? This second plot?
The second part is just to see that the slope is really 1. You know, because if you if you do this, you can really see. And in fact, I think it can be made even better because if you bring the cutoff closer to the horizon, this kink thing goes away, and you can see that the slope of this ramp gets even better than this. And so it really gets to 1. So that was the only point.
What kind of ensemble are you averaging over? I mean, are you taking a small window of R naught past the horizon?
Yes. I'm taking a small window, and the precise details of the averaging does not matter. You can do it on a Gaussian, you can do it on a uniform distribution. It doesn't matter. Okay. So for any of those things, you will find that this is the thing.
Yeah, I just want to know when you say logarithmic spectrum, it's a high energy growth is logarithmic. Is that?
So I think so. This is again a difficult question because the point is that in the BTC case, we have not been able to solve this for very high values of J numerically. So we can solve it for moderately large values of J, but I expect that at very large values of J, it will turn around and become linear like an ADS. This is what I expect, but I don't know. So the point being that, if the J is sufficiently large, I mean, somehow I feel like it's kind of like, the thing has a tendency to go to the boundary in some way. So something like that. So, but I haven't checked it. So,
but the logarithmic spectrum refers to what? I mean, when you said logarithmic spectrum.
So let me just show you a picture. So it's something like this. So it basically keeps, this is omega as a function of, for some n equal to 1 or something, this is omega n as a function of J. You can ignore the left side because it is just a negative J. So it basically just keeps going like this. And then I expect that eventually it will become linear. This is what I expect, but I don't really know. So so we also did it for a Rimler geometry times a compact space. And there the problem is that it never actually seems to pick up for large J because in some sense we are already in the near region, I think. So, but in the BTZ and in other geometries, I suspect that J, if you tune to very large J, I think this behavior will turn around and finally become linear is what I think. Yeah, but it remains to be seen. So, sorry. Yes. So, did I answer your question? Or? Yeah, okay. So, so a ramp of slope 1 in the spectral form factor is usually attributed to random matrix theory, and typical integrable systems have no ramps. Typical integrable systems, and in most things that you would try, generally don't have ramps unless there is unless there is random matrix like behavior. So there's one sort of a counter example to this that I know, which is where you take an SYK model, SYK2 model, which means it's a free theory, but the coupling is you take it to be random. Okay, and then you do an ensemble average. So we are not doing an ensemble average, and our theory is not free. Oh, sorry, our theory is free. So in this particular case, if you do an ensemble average, you find a ramp, but that ramp, it's not a slope 1 ramp. Okay, so the only slope 1 ramp, which is not from random matrices that I know of, is in this context that we have found, and now we have some more. So, okay. So the surprising thing here is that our system does not have conventional level repulsion, at least in this particular case. I'll show you. I haven't shown you that yet, but in this particular case, we'll show that it doesn't have conventional level repulsion, and it's therefore not technically RMT, but we still seem to be seeing a ramp. So the spectrum is of this shape, as I showed you. If you keep all of the n's, or at least a sufficiently large number of n's in the spectrum, the level spacing you can see is Poisson. Okay, so it is not. There's no conventional level repulsion. So, but if you keep only for a fixed n, and you look at this level spacing for just omega 1 comma j, let's say, then you find that there is a very sharp kind of thing that happens in the spectrum. So note that there is kind of choppy because, if you are only looking at 1j or numerics, where at least from the first paper, it was not as good as it is even now, and it's still not that good. So, so this is the shape that you get. And and that's the level spacing as a function of j. And you might kind of, if you are, if you are willing to, if you look at it, you may imagine that this is kind of like an extreme version of a Wigner-Dyson distribution. Okay, so in fact, but of course, that argument is not very tight, because if you take a harmonic oscillator and you compute its level spacing, of course, you are going to find a delta function that is separated from the origin. So there will be no support here. Okay, so there will be no support here even for the harmonic oscillator. So there will be a delta function sitting somewhere. So that's not by itself a very solid argument, but we will see that in the next part of the talk that this is actually sort of correct. Okay, so this interpretation of this impression that we had that this is an extreme Wigner-Dyson type curve may be correct. So okay, so this is sort of the things that I've told you so far from the first paper that we wrote, and so let me just summarize what sort of we learned from there. So the first thing is that the compact directions are crucial, and these compact directions. And this is a feature that one often sees in discussions of fuzzballs, that the compact direction is important. And if you just look at the R and T directions, you don't find anything of this kind. So, and the second thing is that the J dependence of the spectrum getting pulled down in this sort of a quasi-logarithmic type shape was key for the emergence of the ramp. And so one of the things that we can explicitly check is that whether you put it in ADS or in a flat space with a cutoff or box, the spectrum has linear dependence in J, and this is what prevents the ramp. So essentially, the J dependence in both ADS as well as flat space, even if you put a cutoff, it's basically a quasi-linear spectrum. It's more or less like a harmonic oscillator. So you don't see any linear ramp. Okay, and so we expect that this is a universal feature of horizons. Okay, but it is typically not. So one of the advantages that we had was because we were working with this BTC black hole, the radial part is solvable in terms of hypergeometric functions. So the numerics only enters at the very end. Okay, but otherwise you'll have to solve the radial part itself numerically, and that's a pain. Okay, so one other example that we have come up with, where also we can solve things kind of analytically, is to look at a Rindler geometry times a compact space. Okay, so, and there again, the radial part can be solved. At least the radial equation has known special function solutions, and then the numerics only enters at the final stage where you are trying to find this omegas. Okay, so the point here is that the results are qualitatively identical for this as well. Okay, so there is no difference whatsoever. In fact, I'm not even going to show you the plots because they look exactly the same, pretty much. So, and in that sense, we expect that this is a very robust feature of all horizons, and the linear ramp does require a horizon. So let me give you some what one expects in general for the ramp in the semi-classical approach. The ramp in the spectral form factor is thought of as a result of including replica of wormholes in the path integral, and this leads to a smooth ramp. So this is what one typically expects. Okay, so, and if you really were to do a true quantum gravity microstate calculation, you would microstate, and you want to do it also from the bulk side. That's the real challenge. So, well, I mean, from the CFT side also, except for this toy models like SYK, nobody has done it. But from the bulk, it is really quite mysterious how it happens, especially if you believe in the smooth horizon. So the question is, so how would you see this? So you would expect to see the ramp ultimately if you had infinite power, and you could compute this quantum gravity bulk thing directly, you would find a ramp, but also with fluctuations. That's what you would expect because it's somehow supposedly a single microstate. So our calculation does this order 1 violence at the horizon, and but it has this virtue that it shows both the ramp and the fluctuations in one go. So there is something about this calculation, despite its simplicity, that it knows something about the quantum gravity is what I think. Anyways, so the next question is, so we did not see any level repulsion, conventional level repulsion at least. Okay, so right, so yeah, so how do we do that? So the most natural thing, the thing that we did in our previous calculation was that we just set a Dirichlet boundary condition by hand. We set phi equal to 0 at the stretched horizon, and we found a linear ramp. So the most obvious thing, I mean, we should have thought of it when we wrote the first paper, but we didn't, is that the natural thing to do is, especially since we know that fuzzball microstates do not have spherical symmetry across the horizon, and they have profile functions which are functions of this angles and so on. So the natural thing to try is that you have phi, which is some function of the angle, and as some generic choice of profile. Okay, so this is the first thing, the simplest thing one can try. And you can choose, you can make this phi naught, this boundary condition to be generic in some suitable sense by taking phi naught of theta to be Gaussian distributed. Okay, so that's the simplest thing one can do. And it turns out that immediately, so we find that as the variance of this distribution, so this phi naught, sorry, as you choose this phi naught of theta from, theta means any angle, is from some distribution. Yes, yeah. So if once I have some variance for that, yeah, so there is some subtlety here because it's I'm not showing any of the details actually, but so the point is that it's the phase of the Fourier series which eventually becomes a random variable. And we found that these things have been studied elaborately by mathematicians. So maybe there is something there. So even in the Dirichlet case, I did not have to fix the normalization actually in order to get the normal modes. So I just demanded that the field is 0 at some point, right? So that actually does not fix the overall normalization. It fixes a relative normalization because I demanded normalizability in infinity. But between these two things, I still have one freedom left. So here also, effectively, there will be one freedom of that kind. But the phase of the Fourier series is essentially what gets fixed. So I mean, yeah, it requires. It requires a little bit more discussion, but yeah. So and at the end of the day, what you see is that as the variance. But yeah, to answer your question, yes, the variance of the Fourier coefficients. That's right. So as the variance is tuned from 0 to large, this the level spacing distribution goes from this extreme version of this sort of thing that I showed you before, which I will show you once again here. So this is a slightly there it was. This is a slightly more numerically better plot. So the point is basically just that it's essentially a delta function sitting somewhere. So, and you see that the level spacing distribution goes from this extreme RMT to a more conventional Wigner-Dyson type spectrum. And eventually, when the variance is really, very large, it basically reduces to a Poisson distribution. So let me show you some plots. So this is the distribution that we find, and we have many plots of this kind now. I think we have better ones. So this is something that Suman sent me, I think, some time ago, and I didn't really change it. So right. So and if you increase the variance further, you find that it actually reduces to this Poisson type distribution. So and the ramp. So when you have a level spacing like this, the ramp is perfectly intact. That's I should have put a plot here actually, but I forgot. So the point is that the linear ramp is completely intact at variances where the level spacing distribution is Wigner-Dyson-like. And by the time it gets here, on the other hand, the ramp has gone away and it all washed off. So this is the sort of the current status. So and so these last 2 or 3 slides, final ones, are I think I've put a lot of story into that. So please feel free to ask questions. So this is sort of the summary of whatever we have sort of learned, let's say, and at least partly. So the first thing is already mentioned is that RMT type linear ramp cannot happen without Wigner-Dyson or maybe some generalization with some discrete symmetries like Altland, Cernbauer, various names are there. So some slight generalizations of random matrix classes might give you linear ramp, but as far as I know, this is generally a surprising fact. So, but our approach suggests that simple and general ways to generate counterexamples to this. We have some sufficiency conditions for when a deterministic sequence of real numbers, which you can think of as eigenvalues, can give rise to ramps. Okay. So, in fact, we also know that. I mean, if you ask questions, I can explain more. So, the 2 key spectra that we find, one is the linear spectrum, which is harmonic oscillator, and then there is a log spectrum, which is where the ramp is quite linear. And as you tune the power law from n to some alpha where alpha is less than 1, all the way to 0 where you get a log spectrum, you find that there are ramps of various kinds in between. So it's a ramp generating mechanism, this n to the power some number. And of course, we don't have a deep understanding of it, but hopefully because the log spectrum seems fairly straightforward, we'll probably be able to understand something better in the nearby future. And that's that. And so another thing, let me come to that in the next slide. So our results also so another statement that is often made is that the linear ramp is believed to be a more robust diagnostic of underlying chaos than level spacing data. And the reason is that level spacing is supposed to only keep track of the nearest neighbor physics. So here, on the other hand, it somehow knows more about the spectrum. So this is the rough expectation, and our results are also essentially consistent with that. Okay, so those were random matrix stuff, but I think the more interesting thing, at least for me, is the black hole questions. So to get a linear ramp, we need a horizon. So this is sort of the main punchline, and cutoff in flat space or radius will not do. You'll always get a ramp. I mean, if at all you get a ramp, you will basically get the ramp with a slope which is much higher than 1. But the point is that level repulsion, on the other hand, is not such a, as I was saying, level repulsion is not such a strong diagnostic of random matrix behavior. So if you put fluctuations at a cutoff, like in the sense of having a profile, it's easy to find level spacing distributions with repulsion even in flat space. And the key point there is that essentially what happens is that if you have a cutoff in flat space, you essentially have a harmonic oscillator like spectrum, but with some small amount of noise in the energy levels. And if you can explicitly check that if you take a harmonic oscillator, add a little bit of noise to the spectrum, you will find level repulsion. So in that sense, this little fact, I don't know whether it was known. I mean, I've not seen it before, but it's trivial to check. Which is that you take harmonic oscillator, add a little bit of noise to the levels, and you will find that you can find level spacings which are very much like random matrix stuff. So it's I mean, that's essentially what is happening when you put a cutoff in flat space or radius and look at the normal modes. Essentially, because they are, you will find that they are in flat space, for instance, they come from the zeros of the Bessel function, and essentially that's a harmonic oscillator like spectrum, but with slight noise. So that's where this is coming from. So yeah, okay. So but to get level repulsion without horizon, the scale. So this is another feature which I think is interesting, which is that even though you do get level repulsion in flat space with a cutoff or radius with a cutoff, the scale of fluctuations or the phi naught theta that I put in, the fluctuations there have to be macroscopic. But on the other hand, in the case of when you have a horizon and you're putting a cutoff near the horizon, these fluctuations of the stretched horizon are Planck suppressed, in the sense that what I mean is that the scale is controlled by the tortoise coordinate, not the Schwarzschild or the asymptotic coordinate, basically. So, and because of which there is a very natural sense, if you look at the details of the expression, that these fluctuations are Planck suppressed. Did you have a question?
Yeah, I
sure.
have
Sorry.
Sort of. So the question is something like this: that the ramp calculations that people have done.
Which calculation?
The ramp.
Yeah.
Or looking at this spectral form factor, the calculations have been done in a simple random matrix model and in the SYK model.
Right.
Where the dip time, as Rajesh was asking, is exponential of S0 divided by 2. It's half.
Yeah.
The dip time, actually. The time at which the dip
has minus 2s. I think it is the size of the random matrix is in the size of the.
So this is the SYK model. So it is e to the
S0 is the entropy of the ground state.
It's the ground state. Yeah, that's right. Yes, that's right.
So that's what I was looking at.
Yeah, that's right. It
seems to be like to the minus 2s. I'm looking at Steve Schenker's review.
You get not mod of something or mod square.
Yeah, so the mod square in something like this.
Yes.
This part is e to the minus. If this is normalized to 1, the bottom is e to the minus 2s.
So the time at which the dip has occurred.
The time is.
That's what I'm saying. That's what I'm saying.
I was
okay. No. I understand.
But I think, all of these things should be. I think they are all fixable. It's my fault.
Let me finish my question.
Yeah.
So that's a calculation that people have done in the SYK model and in the random matrix theory.
Right.
Is there any other calculation that you know?
Yeah.
So because you are saying all the time that this is a black hole. This is what happens. What is the computational justification for all that?
For what exactly?
For the fact that we are discussing a horizon, for example. How do you know?
I'm putting a cutoff right before the
I only know
horizon.
by
Right? I mean,
SYK model,
understand
there's
the
a
question.
duality, there's a black hole. Okay, there's good evidence. But in
Oh,
general,
yeah. So
suppose
no,
I
I mean,
take a
right.
higher dimensional black hole and compute this type of thing. How do you know all this happens?
So if you compute it for a black hole, I mean, it depends on what you mean by a black hole. So if you are talking about what I am trying to sort of do a proxy calculation for is a bulk microstate of a black hole in full quantum gravity. It's a proxy calculation, but that's what I'm trying to do. So for instance, if you just have a black hole in the bulk, which is a general relativistic system of obviously like what you were saying, it's putting infallic boundary condition with a natural thing to do. But then you will see information paradox.
Right.
So, but what I'm trying to do is, if the spectrum of black hole microstates, a bulk description of the spectrum of black hole microstates, the claim is that the implicit claim of my calculation is that the normal modes of the scalar field with a stretched horizon cutoff can capture it. That's the claim, implicit claim. So, and the question is whether it is true or not. And these results are somehow suggesting that maybe there is something there. That's the only thing. So I think that, yeah, so I mean, you look dissatisfied, but
my point is that, I understand SYK model and its microstates and these calculations there.
yeah,
But that's a very simple model in which
Right.
these calculations have been done, and you have this spectacular type.
right,
People have explained.
right.
Grounds.
Yeah. So the thing there is I think the philosophy is that you're trying to model the high-lying part of the n equal for SYM spectrum, right? That's like a model for that. And it's precisely in that sense, on the bulk side, what would you do? That is the question. So, yeah, I mean, I would also say that our RAMs are equally spectacular.
Okay.
So, but I agree. I mean, I'm not saying that it is a control calculation, but the point is that it's a very simple calculation, and it gives you a result which seems reasonable. So, that's the only sense, yeah.
So could it be that it is generic, even though people may not have the view?
That I think is a possibility, yes.
Yeah, and for the following reason, and this is
Yeah.
just a speculation.
Yeah.
You consider any Sturm-Liouville problem.
Mhm.
You think of it and you put some boundary conditions. Maybe you put one of them as sort of a random boundary condition, like you
Yeah.
said with your profile.
Yeah, then you will not get a RAM. That's the point, because you need the horizon.
Yeah, but the horizon is there in the form of the potential of that Sturm-Liouville problem.
Right.
I mean, in the sense that there is a. So what I am trying to say is that in a way, a random matrix is like a random operator.
Correct. Yeah.
And a random differential operator will have a certain spectrum in a certain range,
So,
which may
yeah.
be mimicking that of a random matrix.
Right.
Provided you put in a certain kind of certain randomness. As you said, you take a harmonic oscillator.
I would say that the observation of the linear RAM, I think that really depends on you could say that it is because of the potential in the Sturm-Liouville problem, but it is, what I'm claiming is that it is a universal feature of horizons. So that's what the statement. So in that sense, there could be large class of potentials which do that, but at the same time, I think it is precisely because there is a connection with, these.
Sure.
Yeah.
I mean, there may be.
So
why it is sort of universal, maybe that.
Yeah. So I do think it is universal.
Mimic a random matrix.
Right.
If you put in.
Right. Yeah.
Essentially, you're computing eigenvalues of a random quantum mechanical problem in some sense, not in terms of random potential, but in terms of some random boundary conditions.
So the randomness in the boundary condition is not necessary for getting the linear RAM, right? You only needed, so that was just engineering the level spacing,
yes.
Right? So and I also want to say that it is not something like it has been tried before because of the fuzzball idea that the profile functions can be arbitrary. So it's like, I think there is a certain Bayesian point here, which is that if you're not trying something by just randomly doing something in order to get it, we are doing something that is in a sense motivated by the fuzzball thing. Yeah. And that's what we are trying to. So in that sense, I think it is not just, let me put it this way.
I'm in a way not saying anything about the physics.
Yeah.
It's like I was just trying to qualitatively understand.
Right.
Just if you have this mathematical problem,
Yeah,
why should it
I think,
show this behavior?
So I think that, yeah, so I think the question is, what we have found is that, like, if you can get a logarithmic spectrum, I think it will always give you a random matrix. Logarithmic spectrum will automatically give you a linear ramp. This is something that we have understood now. So in a sense, the question of what you're asking could be phrased as, what are the kind of potentials which can give you a logarithmic spectrum? So you could ask the same, it's a kind of an equivalent way of asking the question. So, we have some answers, but at the same time, yeah. So maybe, I think I still don't really, so which is why I was kind of emphasizing the fact that these are random matrix signatures, but we don't fully know whether they are really random matrix behavior. So these are there are two signatures that we know of, which is level repulsion, and the other one is this linear ramp. Both you can see here. So the logarithmic spectrum, I think it remained, we didn't know about logarithmic spectrum, that it was, by doing this, we kind of stumbled into it. So, and I think that also is not nothing, but at the end of the day, logarithmic spectrum is very simple. And I think that that's related to the fact that the horizon physics is universal. So that's how I would think of it. And that's the reason why I think we had, the reason why this calculation we started doing is because, we could hope to get something interesting because of horizons being universal. Otherwise, we could not, you would really need something like fuzzballs. I didn't, yeah. So that's so I agree with whatever you're saying in some sense, but at the same time, I think I would cast it slightly more positively. That's all.
Yeah. I'm not. I was just trying to understand. You've shown a phenomenon.
Exactly. Yeah.
I'm trying to understand what could be
Yeah.
the reason for that phenomenon.
Right.
There's some calculation you've done and it shows this behavior.
Yeah.
I'm trying to.
I totally agree with that. I think that, so I would say, yeah, so it's the potentials that black holes produced by black hole horizons is one way to characterize it. And the another way to characterize it that there is a certain sense in which logarithmic shaped spectra give rise to it. So these, I think, are sort of correlated in some way. Yeah. So Ashok had a question. Sorry.
So I'm just trying to understand. So from what I understood from your talk is that you have two separate phenomena which are decoupled. That one is linear ramp, the other one is a level ramp.
Right, that's right.
You can get one without the other.
You are 100% correct. Yeah.
And it seems that if you're trying to understand black hole microstates, the linear ramp is the more significant one, right? The other one is just because you are averaging over microstates, which you didn't have to do.
Well, not averaging over microstates. We are putting if you put a cutoff in flat space, you would immediately get. And you put a profile, some fluctuations you put, if you put the boundary conditions at a fluctuation.
But if you don't average, you are taking the fluctuation over Gaussian ensemble, right?
No, I'm not doing that. So what I'm doing is, so there is no ensemble average. I really want to emphasize it actually. So if I missed emphasizing it, I should say that. So what I'm really doing here is, I'm just taking this phi naught of theta, and I'm taking this phi naught of theta to be a random profile, but it's one random profile.
Okay.
So, and I'm not averaging over anything. And this, for instance, this will be the general shape of the level spacings that I get, and the linear ramp will always be there, etc. Where was it? Here. So this sort of linear ramp will always be there in all of those cases. Is the point? Each realization, exactly. So there is no ensemble average, and but there is there is one point that I wanted to emphasize, which is kind of related to your question, which is that. That we are putting, if you put fluctuations at the cutoff, in the sense that there is a scalar field profile that you put at the cutoff, you don't need a horizon in order to see level repulsion. And that, I think, is kind of related to your point, which is that the linear ramp is a more robust diagnostic, it seems like, than level repulsion. And the second point is that, the point I was making was that this is related to the fact that noise, if you add a little bit of noise to the simple harmonic oscillator, you again find level repulsion. So, and it's exactly that in some sense, because the fluctuations at the cutoff is really moving the spectrum of the zeros of the Bessel function a little bit. That's what it is really doing.
But that won't have a linear ramp.
That won't have a linear ramp, exactly. So, and the second point I would say about that is that in order to even realize this, the fluctuations or the oscillations of the phi naught that you're putting in have to be macroscopic. So in the sense that there's a natural scale associated with that, and that is in the radial coordinate, in the cutoff scale. The cutoff scale is what controls it. But in the case of this horizons, the near horizon cutoffs, it is in the horizon, it is in the horizon coordinate, but the horizon coordinate is a tortoise coordinate. So there is a natural suppression in scale compared to what happens when there is no horizon. So those are two aspects. So yeah, so it is true that the level repulsion can be arranged by having a cutoff with some kind of a profile, but the profile has to be macroscopic in a suitable sense. And in the case of horizon, that's not the case. You can have a microscopic or fluctuations which are Planck suppressed in a suitable sense, but at the same time find a linear ramp. So those are the two punchlines. And the final thing I would say here is that so there is so this is probably a fact that is sort of known to people before, but this is something that I've never come across, which is that if you compute these omegas, what we find is that the level spacing, and this is true actually even for more general black holes, because we found an approximation to do this calculation even for more general black holes in order to count, just to make estimates. We found something with my student, and one of the things that you find is that the level spacing in the J direction is actually exponential in the entropy. The coefficient we cannot fix, but you can, and this is kind of related to your question about the ramp, I think, even though we have not established it, because the slope of the ramp, I suspect, has something to do with this, because it is the e to the, you basically find that it is controlled by precisely the area that, and it makes sense because it is the, the angular directions are what are playing a role. And you find that, yeah, so I think this is an interesting fact, which is that if you put a cutoff and you're computing the spectrum around it, the level spacing is kind of like a black bulk mechanism, right, for creating that the exponential level spacing that one hopes for in the black hole setting. So, and it also says that somehow the stretch horizon size has to be Planck scale. Note that our entire calculation is probe. So in that sense, whenever I say this Planck scale, you should not be fooled. It is really just saying that I'm putting it at a cutoff and I'm calling that my Planck scale. It's a probe calculation in a fixed geometry. So yeah, but once you do that, it is nonetheless interesting that the level spacing is precisely what you might see from what you might expect from black hole microstate level spacing. Okay, so this is the sort of the final slide. So our result can be viewed as encouraging for the Fuzzball program, even though, as various comments were made, there's pretty much nothing directly to do with these BPS Fuzzballs, but I still feel there is something there. So, but the real challenge, in my view, is that it's not that it's operationally well defined as there is nothing, what is a quantum black hole microstate and what does it mean to say that it stops at the horizon is unclear. And the trouble is not that the statement is wrong in my view, but it's not fully satisfactory statement about what the microstate is I don't think it is there. But I do find, so since I was probably harsh to both sides of the Fuzzball debate, I should say that I find the heuristic idea of geometry stopping at the horizon, I think it's stimulating, and there is something there is what I feel, at least after this calculation. So this is basically what it is, and I will stop here. And thanks for your questions. Thanks. Yeah, sure. Thanks. Yeah.
Are there any questions?
Yeah,
Yes.
I have a question. Hello.
Right.
Hello.
Hello.
Yeah.
Oh.
So I have a question. Do you have any idea as to what the holographic dictionary? I mean, what the corresponding boundary theory would look like? Because it would not be like SYK or something like that. Because you have
Okay. So the bound, yeah,
logarithmic.
Yeah, I think the boundary theory is not, boundary theory can be anything, so it's, so if it is a general statement about black holes, this would be it's be a statement about, let's say n equal for superangulars. It's just that you have to look at the part of the spectrum which corresponds to the black holes. But I think there is an interesting question one can ask if this is to be taken literally, which is that what does the boundary, so what we have done is very simple from the bulk, but from the CFT side, it's completely, it's like a magic boundary condition, right? It's an infrared boundary condition. And it is like somehow we have, so yeah, I mean, I'm asking a question slightly different from what you asked, but I think the question that one would really like to understand is there a natural boundary condition in the infrared that you can impose on heavy CFT states when you are doing, let's say a 4-point calculation or a 2 light operators in 2 heavy states. What is the replacement that one should make? So here what we did is, instead of working with the black hole microstate, we made a replacement. We just basically replaced the horizon with some cutoff, and we did something. So what would one do if you were to do a similar calculation on the CFT side, which is that you take 2 light operators and you're sandwiching, the standard heavy light kind of correlator. What is it that you would do? Is there a canonical replacement that you can make for the heavy state? Maybe there is a universal heavy state thing that one can do, which is not quite the thermal state. And I think that we have some thoughts in this direction, but we haven't really thought about it too much. But yeah, so that's sort of answer to a question that was, I don't know why I'm speaking to the mic in this loudspeaker, but yeah, so it's not quite the answer to the question that you asked, but I think maybe this is a better question to answer. Yeah.
First, you said you will be working with fuzzball, but then you replaced fuzzball with some stretched horizon.
That's right.
Can you elaborate there?
I didn't really ever work with fuzzballs. The first half slide, first maybe 10 slides was just motivation. So to kind of sort of get everybody on the same page and maybe get some feedback from Ashok and so on. So it was not. I didn't really work with the actual fuzzballs at all. So, but the point is that the fuzzballs are believed to kind of cap off before the horizon. And in classical supergravity, they cap off, before the Planck length. So in some sense, you don't have access to the Planck scale. And in that sense, that's, I think, kind of like a basic, some of the criticisms that I mentioned. And it's kind of an obvious, I think it is, I don't think there is any way to get around that, because it's a classical solution and you're capping it off before the horizon. But I think that if you really take the point of view that this is a proxy for something that stops at the Planck scale or near the horizon, then I think you could do something like this, which is a by hand replacement of the kind that I'm doing.
Horizon exists or like
so horizon exists means the geometry, the background exists, but I'm cutting it off before, right? So scalar field doesn't get to the. So and also another thing is that if you look at the Susskind-Torlashes Aglom, the title of the paper is Stretched Horizon and Black Hole Complementarity. So stretched horizon is somehow it has kind of fallen by in the decades since, and complementarity without somehow stretched horizon is now seems to be the thing. But I think the original motivation definitely had stretched horizon. That's the title of the paper. So, and I think that it should be taken seriously, somewhat seriously at least. Right. Yeah, please.
So I just had 2 questions.
Sure.
So one question was, if I replace these ADS black holes.
Sorry?
You had this stretched horizon of ADS black holes, but if I had flat black hole, okay, for some dimension.
I don't think it matters. We haven't seen the problem is in Schwarzschild, for instance, the wave equation is harder to solve. So, but I don't think it matters. So we have done 2 cases. One is a 2D Rindler space times a compact space of constant radius. That's one case we have done. It's not quite asymptotically flat, but it's not it's not ADS either. And the second case that we have looked at is this BTC case. So in both cases, we find entirely identical things. So
yeah, but in some sense, both of these are already like hypergeometric, or
well, I mean,
kind of, I mean, some.
Well, I mean, everything is kind of hypergeometric except, so I mean, Bessel functions are a form of hypergeometric in some way. So in that sense, you're right. But I think that that particular Bessel structure is what is ultimately key. For instance, the hypergeometry in the BTC case, it is a hypergeometric function that we find, but eventually the structures that we find are related to some gamma functions, and the structure of the gamma functions of imaginary direction and so on. And those structures are generally present. And I agree that. So let me say it another way. So for instance, you can look at black holes. There is this this Kerr-CFT correspondent that used to be there a decade or so ago, in which people used to do this particular limit or particular approximation where they would drop wave equations. They have wave equations, and then there are certain terms in the wave equations you drop, and then you find that all of them are hypergeometric. So there is a sense in which hypergeometrics might be universal. But you're correct that technically what we are doing has only been done for those geometries for which the hypergeometric type solutions are the ones that apply. So yeah, so I mean, if really you should do a Hoyne equation, then you. But in principle, I think it is numerically possible. But we are very numerically limited in our, that's all. Yeah, anyway, go ahead.
Okay, one more question. If you put this hardwall cutoff, let's say in BTZ, just to be definite, do you have an idea that if let's say, rather than calculate the spectrum, I calculate something like the reflection coefficient or something. Is there a way to get Bose-Einstein factors? I want to know like whether this hardwall cutoff, how well does it reproduce, let's say, Hawking radiation?
So if you can write, that's an excellent question. And I have some thoughts. I would like to write something actually. If is it possible to? So
maybe you can just write there.
Yeah. So I have this claim which I have not completely checked, but I hope is right, which is that let's say you're computing a standard Whiteman correlator with a stretched horizon, which you can do because you have a reflecting boundary condition. So I suspect, this thing is going to be equal to the Hartle-Hawking thing plus e to the minus, a by this L Planck times some order 1 thing. This is what I think is actually what's happening. So it's kind of an eigenstate parameterization type thing is what I think is happening. But you've not been able to show it because but it should be doable. Somebody who is more powerful than me in technical things, I think it should be easily doable. You know what I'm saying? So, but we are kind of struggling with it. But I think, so this is the Whiteman, both are Whiteman correlators. And I'm just computing 2-point functions. So this is with the stretched horizon. This is without the stretched horizon. This is basically the thing that, the boundary conditions are infalling boundary conditions. And I'm computing the Hartle-Hawking function. So, and if I do that, and this is the standard Whiteman function, but with a stretched horizon. So this is what I think will happen. So, but it will be interesting to show this because then it means that, Hawking radiation can be derived without a smooth horizon. That'll be very interesting because except for this, this suppression, I don't know whether this is true, but if something like this is true, it'll be very, very interesting. So, yeah.
I think my question is a classical version of this, that if we throw in a signal, right? I mean, in this with hardwall cutoff, it will come back in certain time, right?
Right, yeah.
And what is the, return time is presumably much smaller than what we expect for a black hole, right?
Yeah, I think, so I think it is, I think if you're sending in waves or something, so I think, so the problem is in some ways, like, I don't know what is a good boundary condition to put for instance, something like a geodesic at the stretched horizon. So I don't know what is a good boundary condition to put. But if it is a wave or something like that, I mean, I don't know. I mean, it's
I'm thinking of just a Gaussian wave packet of 5.
Yeah. So, I mean, it's, I don't have a good, I mean, I mean, I think it's a quantum version, a wishful quantum version of that is what this is. But I don't have a real, we are still struggling with these things and I'm not 100% sure whether it will work also. So, but I think it is a natural, if it was true, it would be very nice. but for the reason that you said, because somehow things may come back faster, I feel like. So that's the problem.
Hi, can I make just a couple of comments, Chethan? Hi, this is Arnav.
Oh, yeah.
So first of all, of course, I agree with, at least I find more than enough things everybody said to agree with. I'm not just being.
I cannot hear. Sorry.
Hello, can you hear me?
Speak more loudly.
Oh, sorry. Can you hear me now?
Oh, yes. Oh, Arnab.
Hi. Yeah. So I just wanted to add one or two very, very quick things. First of all, I agree with essentially everyone. And so two things. No, I'm not trying to be funny or unnecessarily nice, but two things I just wanted. Maybe there's one thing which I'm not sure whether I heard it right, but there was a question on the dip time, which is sometimes also called the Thouless time, and how it behaves for us as opposed to random matrix theory.
Yeah.
And the answer, I think, is, well, I mean, we can do some
I think I can repeat. I think.
Can you speak more loudly?
Oh, I'm sorry. Can you hear me now better?
Can you increase your volume?
Yeah, I increased my volume to the maximum.
But I think I know. I think he's talking about the dip time.
Yes, yes,
Dip
yes.
time. So but I think that yeah, we had a discussion about that, but I'm not really sure about what exactly controls the dip time. So I think it would have been.
So what controls the dip time is, roughly speaking, what people also refer to as sometimes Thouless time, and that is so if you I don't know if you can hear me, but let me just say it. So if you're computing a partition function which is an infinite sum, and you are approximating the infinite sum by an integral, there's an approximation that is being made in going from the sum to the integral, and when that approximation becomes invalid, it's when this curve starts going up. So that is precisely where the dip time is. And for us, it's also like random matrix theory. And I'm not sure if you study that will tell you anything specific about random matrix theory, meaning that you can find many systems where this dip time behavior could scale in a similar way, just simply because of this approximation and when it fails. So that's just one comment. The other thing I'll just say that, I mean, what we are doing is, of course, as Chethan said, is very ad hoc. And in particular, for example, as you're saying that what is this boundary condition from the CFT point of view, that I don't think at least I have an answer or a guess to. But I think, I mean, it might be interesting to understand. Just not just because of black holes, but generally because when quantum chaotic systems can appear as in general. I mean, even if you go slightly away from a black hole inspiration or motivation. Yeah. So very briefly, that I'll be more than happy to elaborate more on some other things. But yes, so thank you. I hope I was a bit audible at least.
Yeah. I think one comment I'll add is that in the case of the dip time, in our case, is controlled by, I think, the cutoff that we're putting in. But I think in the thing that I think Rajesh was asking, whether it is directly related to the black hole entropy, I'm not sure it is. So that's the.
Yeah, that I agree that it is not.
Yeah, it is. Yeah.
Yeah.
Yeah. Right. Yeah. Yeah. So one of the things is that it might eventually actually be in our case also. That is what I suspect now, because of the fact that, now we have a better understanding of what the spectrum is. Before that, it was just numbers because we got it like numerically. So now we understand the spectrum a bit better and we can relate it to the bulk geometry a bit better. So it may be possible, but it remains to be seen. So.
If there are no more questions, let's thank Chethan once.
Thank you.